Today we're going to be looking at how to write nuclear equations. Now, in a lot of ways, it's similar to a chemical equation, but we're focusing more so on the mass number, protons, and neutrons, and we will also be looking at alpha, beta, and gamma radiation and how to express that in a nuclear equation. You might be asking yourself, well then what's the difference between a nuclear reaction or a nuclear equation and a chemical reaction? Well, chemical reactions only involve the outer electrons of atoms and they do not change the elements themselves, but instead they rearrange them or they combine them to make compounds. So here's an example. CH4 is methane, and when that is reacted with oxygen in a combustion reaction, the products are carbon dioxide and water. Now, all the elements are still there. We still have carbon, hydrogen, and oxygen, but they just rearranged. This is different than a nuclear reaction. Nuclear reactions can actually change an element into a different element. And this change means that the number of protons and neutrons are changed during a chemical reaction. Because remember, if you change the number of protons, you have now changed the element. As a quick review, we have already looked at how to write isotope symbols, but let's look at this again. It's also called nuclear notation because we're notating what's in the nucleus. The symbols that we use to represent the atomic nucleus contain information about the number of protons and neutrons. So here is this X, this A, and this Z. So let's go through this step by step. The X is representing the element symbol. So this is the one or two letter symbol that represents each element and is unique to each element. The A at the top is the mass number, and this is the number of protons and neutrons in that specific isotope. Remember that this number can be different for different isotopes of the same element. The Z at the bottom is the atomic number, and this is the number of protons in that element. And remember that the atomic number does not change for a singular element. So whether it's carbon 12, carbon 13, or carbon 14, what makes it carbon is that it has 6 protons, and that 6 is the atomic number. So the X is the element symbol, the A is the mass number, and the Z, or the number at the bottom, is the atomic number. So what does this nuclear notation look like? Let's look at a couple of examples. An alpha particle is a helium-4 nucleus, which contains 2 protons and 2 neutrons. So the way that we write this as an isotope symbol or nuclear notation is with the He, which is the symbol for helium. The 4 at the top is representing that mass number of 2 protons plus 2 neutrons, and the number at the bottom, the 2, is the atomic number of helium. So this all together is representing our alpha particle. A hydrogen 1 atom containing 1 proton and no neutrons can be written like this, where you have your capital H as your symbol, 1 is your mass number because 1 proton plus 0 neutrons is only 1, and the 1 is that atomic number of hydrogen. All right, learning check. Let's see if you're paying attention. So which of the following is the correct nuclear notation symbol or isotope symbol for uranium-235? So take a second, maybe pause the video and see if you can figure this one out. Okay, do you think you got it? The correct answer is B. Uranium-235 is written as a capital U. The 235 is the mass number, so it's at the top, as expressed after the dash. And the 92 is the atomic number of uranium. Okay, A is incorrect because 143 is the number of neutrons, and we do not write that as the atomic number. C is incorrect because this is uranium-235, not uranium-238. And D has the 2 numbers mixed up. So once again, the correct answer is B. So let's go ahead and look at a nuclear equation. So here we have uranium-238 decaying into thorium-234, and it's kicking out an alpha particle or a helium nucleus. So at the top of the uranium is 238. So that's our mass number, or our protons plus our neutrons. And then on the right side of the equation, we have the mass numbers of thorium, which is 234, and the mass number of helium, which is 4. So 234 plus 4 equals 238. So right now, our mass number on the left of the arrow and our mass number on the right of the arrow is equal. So let's take a look and see if that holds true for the atomic number also. So our atomic number of uranium is 92. And remember, we can still get that from the periodic table, okay? Also remember that protons are positive. So right now we have 92 positive charges in the nucleus. On the right side of the equation, we have thorium, which has an atomic number of 90, or it has 90 protons. And we have helium with an atomic number of 2, or there are 2 protons. So right now we have 92 protons on the left and 90 plus 2, or 92 protons on the right. So right now our atomic numbers, or our charges, are also equal. Okay, so we just saw that the mass numbers on both sides of the arrow were equal, and the total charges, or the number of protons on both sides of the arrow, were equal. So we can balance nuclear equations, okay? Because of the law of conservation of mass, we need to balance them. So just like a chemical reaction, a nuclear reaction must also be balanced. So there must be a mass number balance, meaning that the sum of the masses on both sides of the equation are equal, like we just saw in the slide before. And there must also be the same charge on both sides of the equation as expressed as the sum of the atomic numbers on both sides of the equation must be equal. Okay, what does that mean? Okay, so do you remember the 92 versus the 90 plus 2? That's what we're talking about. The 92 positive protons need to equal the 90 protons plus the 2 protons on the right. So we're just making sure that those charges are equal on both sides of the equation. Learning check number 2. So what does the division of the sides mean? We keep saying the right side versus the left side. So what does that mean? A, the plus symbol, is that division. B, the isotope symbols for each element. Or C, the arrow indicating the reaction progress. So which one of these separates the sides? So take a second and make a choice. Okay, you think you got it? The correct answer is C. So when we're talking about the different sides being equal, we're using the arrow to divide the sides. The reactant, arrow, product. So the reactants need to equal the products. Here is an example. We have radium decaying into radon and kicking out an alpha particle. Okay, this is also called alpha decay. So the helium nucleus on the right tells us that this is alpha decay. And we know that the mass numbers, or the top numbers, and the charges, the bottom numbers, must be equal on both sides of the equations. So for the mass number, radium has a mass number of 226, and radon has 224, and helium is 4. So 226 equals 222 plus 4. And then for the charges, as expressed as proton numbers, or the atomic numbers on the bottom, we have 88 positive protons on the left, or as the reactant side, and we have 86 for radon and 2 for helium. So 88 equals 86 plus 2. So this reaction, or this nuclear equation, is balanced. Okay, so this is great and all, but how do I solve a nuclear equation? Well, you can think of nuclear equations like a puzzle. So you know that the mass numbers and the charges must be equal on both sides. So just make it happen. So here we have PO, which is polonium, and we know that we have alpha decay, which is an He nucleus, or a helium nucleus. So then the question mark is, well, what element is this going to decay into? Okay, so let's start with the mass number. Let's just fill it in like it's a puzzle. So the mass number of polonium is 218, and that has to equal something plus 4. So let's do some basic subtraction. So 218 equals what plus 4? So 214 plus 4 equals 218. So now I know that the missing piece, or the missing element, must have a mass number of 214. Okay, at the bottom for the charge balance, I have 84 positive protons, or the atomic number of polonium is 84. So that has to equal something plus 2. So let's do some basic math again. To get that missing piece, 84 equals 82 plus 2. So I know that I'm looking for an element with an atomic number of 82. So therefore, the missing piece must have a mass number of 214 and an atomic number of 82. So looking at the periodic table, the element with an atomic number of 82 is lead. So making the final equation, polonium decaying into lead plus an alpha particle, or through alpha decay. Here's another example, but this one is beta decay. So here we have lead decaying into some other element plus a beta particle. And remember that a beta particle is an electron. We also have gamma emission, but the gamma rays is actually just energy. And so that energy does not change the nucleus of the atom. So let's start with the mass number to figure out what this is. The mass number of lead is 214, so 214 has to equal something plus 0. So the 0 is because the relative mass of an electron or a beta particle is 0. So 214 equals 214 plus 0. So I know that the mass number will stay the same for our mystery element. Now let's look at our charge balance, okay? So lead has 82 positive protons, and that has to equal something plus a -1. So what is this -1 business? Well, remember, it's an electron. And so since it's kicking out a negative charge, then we need to keep our overall charges balanced, okay? That's why we think of this in terms of positives and negatives, not necessarily just atomic numbers. So the charge balance, or lead has a atomic number of 82, meaning that there's 82 positive protons, and that has to equal something plus a -1. So 82 is going to equal 83 plus a -1, because 83 minus 1 equals 82. So that must mean that the atomic number is 83. So therefore, the mass number will still be the same since the mass of a beta particle is 0. The overall charges must balance. So since an electron has a -1 charge, the atomic number, or the number of positive protons of the missing piece, must be 83, since 82 equals 83 plus a -1. Then finding the element with an atomic number of 83 is bismuth, making the nuclear equation lead 214 decaying into bismuth 214 plus a beta particle. And overall, it's a beta decay with gamma emission. So it's time to do some practice. So here are 3 nuclear equation problems that you can practice. You have number 1 with alpha decay, number 2 with beta decay with gamma emission, and remember that the gamma emission does not change the nucleus of an atom. And then number 3 is alpha decay, but also look and see that both pieces are missing for that third alpha decay. So that third one, you're going to have to add in the alpha particle and find the missing piece. So take a few minutes and do that now. On the next slide, I'm going to have some answers for you, but don't cheat. Actually try it out. Here are the answers to the practice, so check your work, and if you have questions, then ask me when we get back to class. And here's a little nuclear chemistry joke to finish up our nuclear equation notes. What did the nuclear physicist have for lunch? Fish and chips. Do you get it? Haha. Have a great day, guys.